Welcome to lecture 32. In this lecture, I want to talk about Hawking radiation. Recall that in lecture 31, we discussed black holes. It was also mentioned that black holes are not entirely black, something that was figured out first by Stephen Hawking. So black holes do emit something, and the something they emit is known as Hawking radiation. Hawking radiation is an effect that arises from combining quantum mechanics with gravity. This is different from quantum gravity, which to this date eludes us. It is simply putting together gravity, classical gravity, and some regime of gravity where it has an effect on quantum mechanics observables. In this lecture, we will calculate that effect. We will calculate properties of Hawking radiation, and we will do so in the present lecture. To get started, let us review some properties of the Schwarzschild solution to general relativity. First, note that it is a static and spherically symmetric solution to Einstein field equations. And we found that in spherical coordinates, we can write down the Schwarzschild metric in the following form. So there's a term that is proportional to the time lag component of the metric. There is a radial component of the metric, and the angular components of the metric is just the usual angular coordinates. This factor a of r here is a radius-dependent function, and it's given as 1 minus rs over r, where r is a constant. And this constant here has the meaning of the so-called horizon of the Schwarzschild metric, and it is given by rs is equal to 2gm. So this Schwarzschild metric here indeed has a coordinate singularity at the horizon. So when r is equal to rs, because then this Schwarzschild factor a of r becomes 0, and it means that the metric is no longer invertible. And we want to tease out some more properties of the Schwarzschild metric close to the horizon. Just to give you a sketch of what's going on, so the Schwarzschild metric describes essentially an empty spacetime outside of the so-called event horizon. This was the Schwarzschild horizon we had in the previous slide. All the mass that is in the spacetime is inside the black hole. It's basically residing in the singularity here at the center of the black hole. And the event horizon is given by r is equal to rs. And we will be concentrating on this regime close to this event horizon. Just to reiterate, this is called a black hole because photons that get sort of emitted, for instance, very close to the horizon, basically have to climb out the very steep gravitational well, and they lose all their energy. So they only make it out as black photons. So they have no color at all. So that's why it's called a black hole. So before jumping into the math and calculating some properties of this Hawking radiation, let's give the physics gist of what Hawking radiation is first. So you have heard that in quantum field theory, there's a process that's known as pair creation. What pair creation is that because of the quantum uncertainty relation, it is possible for a particle-antiparticle pair to pop out of the vacuum, so out of nothing, for a brief period of time. So this is allowed because having a particle-antiparticle pair is equal to basically some amount of energy. Basically it's the energy of the rest masses of the particle and the antiparticle, as well as their kinetic energy. And you can borrow that energy for a brief moment of time, delta t, such that the energy times the product of energy and time is basically limited by h bar over 2. So the larger the energy that you borrow, the shorter the time is that you can borrow the energy from the vacuum. After the short time is over, the particle-antiparticle pair has to annihilate back. So basically it will annihilate into pure energy, and the energy just goes back to the vacuum where you took it out from. Essentially, this is a physics way of taking on a zero interest mortgage from the bank, So you take out money from the bank for a short amount of time, you don't pay any interest, so you just give it back to the bank after you're done. So this works well, and sort of we think it happens all the time in usual spacetimes because of quantum field theory, and that's good and nice. But at the moment, I want you to concentrate of what happens if such a process, namely pair creation, happens very close to the horizon of a black hole. So if that happens, it can be the case that that one of the particles just falls into the black hole, whereas the other one does not. If that happens, the one that has fallen into the black hole can no longer annihilate with its partner because one of them is inside the black hole, the other one is outside the black hole. They have no means of communicating with each other. If the other particle then, well, if the other particle falls into the black hole, there's nothing that happens, but it can be that the other particle just has enough energy just make it out of the gravitational well of the black hole, so it can escape potentially. If that's the case, then it is a real particle with a mass, potentially a mass, and some kinetic energy, and that energy has to come from somewhere because energy is conserved. So what that means is that the particle's energy, the particle that makes it out, this particle's energy must have come from somewhere, and the only place that it can get its energy from is the black hole. So essentially, the story is that in quantum field theories, particles can borrow energy from the vacuum. They have to give it back. Normally, they do that by just annihilating and giving back the energy to the vacuum after they are done. However, if one of them is, or if they're close to a black hole, it so happens that it can happen that one of the annihilation partner falls into the black hole. So the annihilation process is no longer possible. And what that means is that the remaining particle can escape, and it does. If it does so, because energy conservation must still apply, the only source of energy that is available is the black hole. So the black hole basically pays the mortgage for the particle that has escaped. So because the black hole has to basically pay the energy that has ended up in the particle that made it out, the black hole basically loses energy. Because it loses energy and energy is equal to mass, that means that the black hole loses a little bit of mass. So that's the story. So that's basically the physics intuition about what Hawking radiation is. But we want to sort of dig a little deeper and also derive the mathematical process using some of the tools that we have at our disposal. So to get started, recall that we have the Schwarzschild metric. It's given in equation 32.1, and it has this coordinate singularity close to or at the horizon, r is equal to rs. In the following, because this is where all the action happens, we want to focus on the region very close to the horizon. So to do this, we sort of make a coordinate change. We change the variable r into new variable rho in the following form. So this is a nonlinear transformation, but that is not important. And we want to focus on the region that is very close to the horizon. So we want to rho, or we want to approximate rho to be much, much smaller than 1. If we do this variable change and we plug it into the Schwarzschild metric 32.1, we find the following form. So r has vanished and it has been replaced by rho at all instances. Particularly the Schwarzschild factor here becomes 1 minus 1 plus rho squared. And the dr squared becomes this term here, where it's now rs squared, 4 rho squared, d rho squared over rho squared. And the angular part where we had an r squared just becomes rs squared, because we assume that we're very close to this horizon here. Clearly, that simplifies if we sort of cancel all the terms that cancel, and we find a simple form for the metric very close to the horizon. So that's what we find. If I pull out the 4rs squared, then this is the metric. This is the metric very close to the horizon. And I want to now sort of use a trick from thermal quantum field theory, where instead of having time be real, I want to make time to be imaginary. So I make another variable change from real time t to imaginary time tau. And I do this because this is a well-known trick in thermal quantum field theory that then says that if I do this and if I take tau to be periodic with respect to inverse temperature T, then this gives me the quantum field theory in a thermal bath. So T here is the temperature of the system, and tau is periodic with respect to this inverse temperature T. So basically what that means is that this term here, the term that usually used to be minus rho squared over 4 rs squared dt squared, just becomes plus rho squared over 4 s squared d tau squared. The rest of the metric remains unchanged. However, if we concentrate on this part of the metric here, then this looks somewhat like the metric in polar coordinates. Okay, so we have something that is the piece that looks like d rho squared in polar coordinates, and then in polar coordinates we have rho squared d phi squared with the angle phi. So basically, by saying that okay, these two things look very similar, we can identify tau to be some sort of angle here, or rather, we can identify tau over 2rs to be equal to some angle phi. So think of this as another variable change. If we do this, then we want phi, the angle phi, to be periodic with period 2 pi, because if it's not periodic with period 2 pi, then well, either one of these metrics here is not a simple manifold. Basically, okay, let's sort of back up. If phi is periodic with period 2 pi, then the polar coordinates just describe the Euclidean space R2. So this is a Euclidean manifold. It's a flat space in 2 dimensions. However, if phi is not periodic with respect to 2 pi, the space is not quite flat. Basically, it is a space that has it doesn't look like a plane, it looks like a cone, because the angle to go around is not quite 2 pi. So basically, you have a cone, and if it's a cone, then the cone will have a conical singularity at rho is 0. This is not a coordinate singularity, this is a real singularity, and it would mean that the space-time has a real singularity at this point, rho is 0. This is, to the best of our knowledge, this would be unphysical. So we want to, at all costs, avoid a conical singularity. So that means the only choice that we have is that this angle phi here has period of exactly 2 pi. Okay, so in order to avoid the conical singularity, we must have this periodicity condition in terms of this imaginary time tau over 2rs is periodic with respect to 2 pi. But recall that I also said that tau also has to be periodic with respect to the inverse temperature. So then, since we can't have two periodicities, these two periods must be the same. So we find that 1 over tau has to be equal to 4 pi rs, or the temperature has to be equal to 1 over 4 pi rs. If we plug in the value for the Schwarzschild radius rs here, that means that the temperature has to be 1 over 8 pi gm. So what is this temperature? This is nothing else but the Hawking temperature of the black hole. So we find that the black holes that are given by the Schwarzschild metric do in fact radiate. They radiate with almost, or basically a perfect black body spectrum. And the black body temperature is given by the Hawking temperature of the black hole, which is given as 1 over 8 pi gm. Note that the Hawking temperature is proportional to the inverse of the mass of the black hole. So what that means is that a very large mass black hole has a very, very small temperature, because small temperature also means small power of radiation. This means that very large black holes radiate very, very little. Turning it on its head, it means that the smaller the black hole is, the hotter the radiation will be, and the more the black hole is actually radiating. So the logical conclusion of this is that if you have a black hole that's left to its own device, it will radiate, and as it radiates, it shrinks because it has to supply energy to this radiation. By shrinking, it becomes less massive, so it gets its mass decreases. But because the temperature is inversely proportional to the mass, the lighter the black hole gets, the hotter its radiation will become, so the more it radiates. So what that means is that black holes radiate more and more power as they shrink further and further, such that eventually the black hole will just evaporate. It is not a stable ground state of matter, it will just evaporate into thermal radiation. That's the fate of every black hole, but you can calculate that for typical astrophysical black holes, even if they're left on their own devices, this will take a very, very long time. And this concludes the present lecture.